All right, so let's write the hydrolysis reactions for these compounds. So we have aluminum nitrate. Aluminum nitrate comes from aluminum hydroxide and nitric acid. This is weak and this is strong. So we are going to cross out the strong. This is our reactant row. This is our product row. So the hydrolysis reaction for this would be, remember I'm ionizing these. And then on the other side of the arrow we would have aluminum hydroxide plus H+. Now this is unbalanced and you need to balance it. So that would be the proper hydrolysis reaction. It would be an acidic salt because hydrogen ions are in excess in the solution. What?
No,
This
the
is
acidic salt
tied up. This is not breaking apart, so it's not affecting the pH of the solution. This is the only thing that can affect the pH.
The
of
acidic
the
salt
solution.
is referring to the original thing, right? Not
Yes,
the-
yes,
yeah.
the
I
acidic
think
salt.
that's what you said.
Yes, thank you. Very nice.
Oh, I thought you were writing.
No. I'm talking about this started out acidic.
Okay.
All right, so the parent here is KOH and carbonic acid. This is strong, this is weak, crossing out the strongs. It's our reactant row, our product row. Starting out with water plus carbonate ion is going to yield us OH plus the weak acid, carbonic acid.
I feel like I can never get the oxidation numbers of polyatomic ions down.
It's just memorization.
I know, but I feel like I've memorized them before, and I just kind of.
And they just fall out of your head?
They're almost all lines.
I wish there was some sense to
I just
them,
know.
but there's not. You could draw a Lewis dot diagram.
It's true.
But some of those are kind of tricky. Okay, this is the tricky one for this set of problems. This is, and this is, this is,
Water.
so the only thing left here is water, and so this one is neutral. All right, now, did we do the NH4? No. I want to show you this. So this is NH4OH. This is HCl. This is weak. This is strong. Everybody agrees with that, correct? This was one of those things from that sheet, things I need to know for the AP test but don't get. NH4OH will not stay in solution like that. It'll outgas, and you will get NH3 plus water. This does not affect the pH of this salt. The pH of this salt is still acidic. And when you go to do these problems, when you're doing an equilibrium situation, as you will in just 2 minutes, this is going to be the reaction that you're looking for. I just want you to see, without your little four-square stuff and everything else that's to follow, this could be kind of confusing. But remember that this doesn't exist like that as a product. It'll do this. Okay, let's move on to why we're figuring this out. All right, so now we talked about your crossing out strongs, you're good with that. Let's talk about what happens if you have two weak acids and two weak acid-base combos. You need to compare the Ka to the Kb. All right, if the Kb of the base is larger, then the salt is going to be basic. If the Ka of the anion, the acid from which it came, is larger, then it's going to be acidic. So all of this boils down to why we wrote the hydrolysis equation in the first place, because somebody who is nasty, could be me, is going to ask you to calculate the pH of a salt solution, because not all of them are neutral, and some of them have a pH that becomes significant and really can change the solution. So step one, which used to be really hard, is write the net ionic equation for the hydrolysis. From that, you can write the equilibrium expression, which is not very difficult to do for you. You can do these every day of the week. Step three is find Ka or Kb using Kw. Very unhelpfully, the problem will give you Ka if the solution is basic, because there's a weak acid involved. And if the solution is acidic, they will give you Kb. All right, how do you do that? Well, you remember and tucked in your back pocket this equation, Kw, the autoionization of water, is equal to Ka times Kb. This, at constant temperature, 1 times 10 to the negative 14th. You can treat this as if it were a constant, and you can easily convert if you want to know Ka, then it would be that. Likewise, if you wanted to know Kb. All right, so these are not going to confound you in the least now. You're going to be really good at these. Calculate the pH of a 0.30 molar NaF solution. See, look at 2 numbers. That's all you get. The Ka value for hydrofluoric acid is 7.2 times 10 to the negative 4. So you are supposed to carry forth with that right now, and you can. Not a problem. Step 1, write the net ionic for the hydrolysis. Okay. I have NaF. The parents are NaOH and HF. This is strong. This is weak. Crossing out the strong. So my hydrolysis reaction for this is there's water involved plus the fluoride ion yields OH plus HF. Now, write the equilibrium expression, okay. Kb, since this is a basic salt, is equal to remember that the water will not participate in the equilibrium expression because it's a pure liquid. Now, I've been given Ka, so I will convert to Kb. Kb is equal to Kw divided by Ka. Kb is equal to 1.39 times 10 to the negative 11. So I'm all ready to go for a rice table. My initial solution is 0.30 molar in the fluoride ion. I have no hydroxide, no hydrofluoric acid. The change at equilibrium looks like this, and my equilibrium equation is this. Popping into the equilibrium expression, 1.39 times 10 to the negative 11 is equal to x squared over 3. We love these problems because the x is negligible in all of them because 1 times 10 to the negative 11 has equilibrium far over here. Okay, so X is equal to 2.09 times 10 to the negative 6th. Remember, that's the hydroxide ion concentration. That's also the concentration of the hydrofluoric acid, but we don't care. So we're going to find the POH. And the POH is 5.69. So the pH will be 14 minus 5.69.
Wait, what is that? What do you find the pOH of? Just
I'm
the
finding
OH
the
ion?
pOH of X.
Which is the
So-
OH ion?
Uh-huh.
Okay.
So the pH is 8.31. This is tricky. I imagine if you went around and polled all the chemistry teachers here, they'd be kind of like, I forgot.
So if they're weak acids and weak bases, how come it dissociates in the net ionic equation?
This is questions bugging you, isn't it? Why is this controlling the pH?
No, but well, because the K is bigger than the acid's K, right? But why is that necessarily dissociating? I thought only strong bases dissociated.
They only dissociate completely.
They did dissociate completely, and this is the remnant of the strong base in the container.
Okay. All right.
You know what, sometimes I just like to draw myself a little beaker and remember what's in that little beaker. Because otherwise, that's when people ask about, well, why isn't it over here? Well, it is. All right, the salt of a weak acid, exercise 22. Calculate the pH of a 0.1 molar NH4Cl solution. The Kb value for NOH3 is 1.8 times 10 to the negative 5th. Look, they gave you a little heads up that something funky is going to be going on here. So doing our four-square method, hang on, they tell us NH3 is somehow involved. The parent here is NH4OH and HCl. This is weak, this is strong. Crossing out the strongs, this is my reactive row, this is my product row. So my hydrolysis equation.
We did this earlier.
Yes, we did. Is so you can look at that and say this is going to be an acidic solution. Everybody good there?
Yes.
And then we added that added caveat that this never stays like that. It ends up like this. So this would be another way to write the products. And we will go ahead and keep this as our hydrolysis reaction. So we have our hydrolysis reaction. When we go to use our rice table, remember all we're going to use are those things that will be in the equilibrium expression, which would be, the waters will not be players here because they're pure liquid waters. What we will need is a Ka value, and from this Kb, so it's 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th. That's 5.6 times 10 to the negative 10. Our Ka expression is going to be our products over our reactant. We're ready to put into our rice table. X is equal to something that is on another piece of paper. 7.46 times 10 to the negative 6. Remember, that's our hydrogen ion concentration. It is also our ammonia concentration. The hydrogen ion, so pH is going to be equal to the negative log of 7.46 times 10 to the negative 6, and that will be 5.13.
I'm just wondering, it said earlier in the notes that Ka will be given if the solution is basic, and Kb will be given if the solution is acidic. But like the Kb is given, but it's acidic. Oh, but you said it was
So that you can find.
But the Kb is bigger than the Ka, so doesn't that mean that the Kb is basic?
No, because you're still, remember, you have a strong in here. They're not 2 weeks. There is a strong
Oh,
here
there is
in
a
this.
strong?
Yeah, it can't, remember the HCl is strong. The HCl is controlling the pH of this solution. It's dumping far more hydrogen ions in than the NH4OH is dumping in hydroxide.
Did we do a 2-week base thing? Oh, 2 week.
And I'm not going to, because
Oh.
AP isn't going to do it to you. You know, I think what's happening to you is you come back to the very beginning of these notes, and this is what's bugging you right here. So we'll talk about that in a minute again.
All right, I thought we were doing 2 weeks.
2 week, So far, I've just done a strong in a week, and I don't think anybody gives you, the only way I think you're gonna see 2 weeks is just in a comparison with a chart like step D has. They're gonna give you a couple of weak things, and you're just gonna have to look. And if this was 5.6 times 10 to the negative 10th, and this was 1.8 times 10 to the negative 5th,
This case.
you're gonna say it's acidic.
All right.
Okay.
So it's just a
That's just a
conceptual-
comparative thing, yeah.
Okay.
Conceptual. Okay, I'm gonna leave this one alone. When I pulled this problem, I think I just looked at this. And then, I don't know what this Ka value for that is, and I think this is, well, I do know what this is. This is complex ion, and I don't wanna muddy the waters, because I think, in my estimation, I think people have a pretty good handle of this. So let's just call this, never mind, and move on. There are enough practice problems elsewhere. All right, now I want to talk about how an acid and a base are made. You take an oxide, and if it's a covalently bonded oxide, i.e. 2 nonmetals, and you put it in water, you make an acid. If it's an ionically bonded oxide, that would be a metal and a nonmetal, you put it in water, it makes a base. Well, isn't that interesting, I guess?
That's crazy.
It is crazy. All right, a Lewis acid and base model, I talked about it just really quickly. The definition of Lewis acid is it is a compound that can accept a pair of electrons, and that's what's forming these really awful coordinate covalent bonds. And then a base can donate. And I talked about this when I gave you the definitions. So here is the coordinate complex being made. Remember, BF3 is a violation of the octet rule. It only has 2, 4, 6 electrons around the central atom. It's looking for 2 more. Ammonia can furnish those 2 more. So ammonia is acting as a base, and this is acting as the acid. So together they bond to form this really not friendly thing. And well, not to me. I just don't even want to. Can you imagine naming that?
Don't judge a book by its cover.
Don't judge a book. Okay. All right, and here we go. Here is aluminum that has lost 3 electrons. It could accept 3 electrons. Here is water acting as a Lewis dot base, forming this ugliness.
Yeah, that looks.
Yeah, you should have just left well enough alone.
What is that? 6?
What I think you're going to be asked to do, if at all, is just to go from a Lewis dot diagram and determine whether something is a Lewis dot acid or a base. So for pH, all you have to do is draw the Lewis dot diagram. So for pH 3, it would be this.
Oh, let's see.
For BCl3, it would be this. This. And then only the last one is interesting in my estimation. Okay, now here's the Lewis dot diagrams, bibbidi bobbidi boo.
So you will let us draw those lines for the electron?
Yeah, because I'm too tired today to draw lines.
Yeah.
You can, I wouldn't on the AP exam, you want them to know that these are a non-bonding pair.
Okay.
Don't be lazy, just be fast. All right, this has some electrons to donate, so it's a base. This has room for electrons, so it's an acid. This has electrons to donate, it's a base. What are you going to say about this wild child?
It's neutral.
Nope. Nope. Come on, somebody be thinking.
It's beyond 14.
So-
Yeah, see,
That is correct. Why?
I have no idea. I just got.
Well, because it's
Because you
easier to
get a
add
50-50
one.
chance.
Oh, 'cause
It's
you
easier
can
to add
add-
one
you
than
can-
to take one away. It's so
What
strong.
period is sulfur in?
That would be 3.
And I can have
You can
more
add the
than,
diagonal on top.
8.
Yeah,
It can have an
more than-
expanded
Yeah.
octet,
Check that
so
out.
it can act as an acid.
And wouldn't taking one of those take away from its octet?
No, you're adding to it.
No, I know, but if you were to take one, it would
Yes.
be hard.